Now we want to talk about some effects you can see using programs like Matlab, like Octave, like Excel, or like Calc. They are also using floating point numbers, every kind of electronic tool, whichever programming language, whatever you do, there are integers, okay, but often there are floating point numbers, and all over there are effects you would not suspect. And in this video I want to show you some interesting things you should wonder about. This should be the first reaction, and the second reaction should be remember them and avoid them. The first thing I want to talk about is something you can observe using Matlab. This is exclusively Matlab. Type in the commands in Matlab format long, then more digits will be displayed format long, and then type in A is 16.1. I did that standing in front of a class, and then I saw that, and then I said, oh, I have to think about this effect next week. I will explain you in the moment. I can't explain what I see. I typed in A is 16.1 and on the display was 16.1, 000 and a 1 following. A 1 following, and that does not make any sense. How is that possible? Let's count the digits. 13 zeros, 1, 2, 3. This is the 17th digit. And what can we say about the 17th digit? Displaying 17 digits does not make any sense because only 16 digits are valid numbers. Why is that true? If this is the line of all the numbers, then using floating point numbers, we have only a finite set of available numbers. And let's see what are the available numbers around 16.1. If this is 16.1, 16.1 cannot be stored as 16.1. It's not an available number. So we will store 16.1 as the next available number. And what are the available numbers next to 16.1? Right to 16.1, this is a number available on the line of all numbers. And left to 16.1, we have the number. We have this number. This number is more close to 16.1, so 16.1 is stored as this number. And storing it in the variable a, and then Matlab says, okay, I want to display what is stored in a. The logic is take that number, and then Matlab says, okay, if the number is between 10 and 100, then we will display this amount of digits, and this is a very bad decision because it should be 1 digit less. It should be 1 digit less. Why? Because if we show that number, this is more or less a random number. It has nothing to do with what the user intended. What should Matlab do? It should display 1 digit less, and in this case every problem is healed. There is no more problem. Let's have a look in my script where I also talk about this effect in a little different way. Okay, type in Matlab these commands, and what do you see? You see that. And what's going on here? You can get all information. Format hex 16.1 is stored as this number, and that means that we deal with that sequence of bits. This is the floating point number as it is stored on the computer. And now we can interpret this sequence of bits, and this is the interpretation. And here this number is 1027, and then we have a subtraction of 1023. We talked about that in some previous videos. And then we see this sequence following. This is 0 times a half, 0 times a quarter, 0 times 1 over 8, 1 over 16, 1 over 32, 1 over 64, 1 over 128, 1 over 256. That's what we have here. And then this one is 1 over 512. This is 1 divided by 4096, and so on. I used not Matlab to do that calculation. That would not make any sense, but I used a computer algebra system, so I can have as much numbers as I want. And doing that calculation, I found out that 16.1 is stored as this number. Then we can find out what is the number left to this one, and then we know, okay, 16.1 will store to that number because it's more close. Okay, this is the analysis. And then very interesting, pi. Everybody knows pi. There are people who know by heart 1000 digits of pi, and here is also a funny story. This is pi divided by 10, and this is how it is displayed in Matlab. It's not displayed in that way in Octave. They have a different approach. This is the way pi is displayed using Matlab. You see here 1 digit more than here. This is not really logical, but it's the way it's implemented in Matlab. It has only to do with display, not with the internal structure. And then if we have a number between 10 and 100, then even one more digit is displayed, and this digit should not be displayed. It's more or less a random number. And in fact, the last digit is incorrect also for pi. Correct would be a 2 and not a 1. In Octave, you can't see that phenomenon. They thought longer about what does make sense, but in Matlab, unfortunately, they made a very bad decision. Okay, let's talk about a second example. The problem comes here from the nature of floating point numbers, and every programming language, whichever you use, you will see the same nonsense return. Here we have some logic. Using n is 9, we can go in steps of 1 divided by 9, starting from 0, and then we can build this array. 1 over 9 is 0.11111, so we build this array starting with 0, then 1 divided by 9, then 2 times 1 divided by 9, and so on. And if you do that loop, that means go these steps as long you are smaller or equal to 1. And it's obvious that if you go in steps of 1 divided by 9 times, you will get exactly 1. And due to that fact, everybody expects that the 1 will be in the end a number in this array. But doing this addition, there will be a rounding effect, and so instead of having a 1 after 9 steps, we will have a number very close to 1, but unfortunately a little larger than 1. So this while condition will not hold true, and so we lose this 1, and we will end with 0.8888. That is very interesting, and I would never have expected such a thing being a student. But now we know this is a very risky programming, and you should never do things like that. Interestingly, in Matlab we have this command, and knowing the problems above, one should expect that here also the 1 will be missing in the end, but surprising to me is that it does not fail. If you don't know very much about floating point numbers, then you are not surprised. If you know the nature of floating point numbers, you are surprised that here everything will go well. And I'm really interested for the explanation why. How is that implemented? What is the logic? What's going on in Matlab, in Octave, if somebody types in this command? Why is the one part of the array and why it is not excluded? It's nice that it's not excluded, but for me, this is really surprising. Okay, this is our example 2, and now let's talk about example 3. Using the following command, if some variable 1 is equal to some other variable 2, is a very risky kind of programming. If this is a floating point number and this is a floating point number, this check should never be done, as we saw here. Because due to some small rounding errors, variables may be very close and only slightly different, and the difference comes from the rounding, and so this programming is very bad and your program most likely will fail. What should you do instead? You should consider commands like that. Take the difference. This will be a small number, maybe a positive small number or negative small number. So take the absolute value, so you have a small positive number, and then check, for example, 10 to the power of minus 12, which you can write in that way, at least in Matlab, and that is much better. But in which range is variable 1 and variable 2? If this is a very large number, then this is not a good programming. Then you should exchange it to 1e minus 6 or whatever. It should consider also in which range are variable 1 and variable 2, and so you can think a very long time. This is only an idea, but it's not helping in every situation. So let's talk about our last example here. Let's talk about Excel, a tool everybody knows, a tool everybody used, and a tool everybody will use several times. Excel is a commercial product of Microsoft, but there is also Calc, which is for free, and it follows exactly the same logic as Excel. Calc is more or less a rebuild of Excel. And now let's see what happens if we type in Excel these commands. The fraction 11 divided by 12 and the fraction 10 divided by 11. These are two numbers which are very close together, as we can see here. If we subtract these two values, then we get a small number, which is 0.0075. This comma is in the German version. In the English version, it would be a point. Okay, if we subtract 11 divided by 12 minus 10 divided by 11, the exact answer is 1 divided by 32. But if we have 1 divided by 132 in A5, in cell A5, then you see we have a 7 or we have an 8 respectively. And what happens if we compare what is in cell A4 and A5? If it's equal, we want to write on the screen equal, and if it's different, we want to write different. And doing that in Excel, the result is different. Although A1 minus A2 is 1 divided by 132. But what is the reason? We subtract two values which are close together, and so we get a rounding error. And we can see that rounding error. And Excel follows the logic, okay, if there is the command compare, then I compare the bits, and if not all the bits are equal, then the content of the cell is not equal, it is different. So a logic behavior. Let's do the same in Calc. I expected that they will behave in the same way, but that is not true. Excel tells us that the two values are equal. Is it true that they are equal? Yes and no, it depends on the point of view. The subtraction is indeed 1 divided by 132, but doing that with floating point numbers, as every program does, then it's not equal, and then the comparison should give a different. So that's very, very interesting. Okay, here in the text is again what I said. But I gave you an advice above, and that is don't type in if variable 1 is equal to variable 2. Never do that, but instead take the difference, take the absolute value, and then compare if this number is a very small number. 1e minus 6 means 10 to the minus 6, which is 1 divided by 1 million. And if the two values are close enough, 1 divided by 1 million difference, then we can say, okay, they are very close. Most likely they are equal. They are very close. And programming it that way, it will make no difference if we use Excel or if we use Calc. But if the two values are not equal and the difference is less than 1 divided by 1 million, then we will get very close. So this is the nature of floating point numbers, and this is the situation we have to deal with. Okay, so that's what I wanted to say, and I think I gave you several examples with commercial products, and you see the nature of floating point numbers is present all over, and you have to deal with, and you have to be aware of the effects. What can happen? Why does it happen? And what can I do to avoid the effects I don't want to see?